All right, let's get started with the two memory models. Oh yeah, let's just let the last few people settle down. My name is Anders. I am a developer at Squarehead in Oslo in Norway, where we work on these acoustic drone detectors. So it's like detectors for drones that work purely based on sound, so that we don't have to emit a radar signal, and we can even catch them if they fly with fiber optics and stuff and don't have a radio signature. So that's what I do during the day. I also run cppquiz.org, a C++ quiz website. And last year, I released this book, C++ Brain Teasers. So if you like to understand how the language works and how things work under the hood, this is my book about a few of those things. And here's 30% off on the ebook if you would like to have that. You can just ask me for it later as well. Today we're talking about the two memory models, and the first question is then like why? Why did I make this talk? Why are you in this room? Why do I at least imagine or hope that you're here? What do I want to tell you? Firstly, you could say you can get some theoretical background for how to work with memory models and concurrency and stuff, but more importantly, I think, is to get an intuition of like what's actually going on under the hood. How do these things work, so that you have like a way of reasoning about this when you get into like doing this in practice. And almost all the talks I write is just because I think it's fun to like know how stuff works, right? So I think this is fascinating stuff. So I hope that you also think it's fun to learn about things like this. Yeah, before we start. Questions, if anything is unclear on the slide, please let me know at once. But for questions about more info, please hold those to the end of the talk. Right, so I've said a couple of times the two memory models. So which memory models are those? The one that you will interact with is the one that your programming language has. So whether you're writing C++ or C or Rust or whatever, your programming language has a memory model. And that's the contract between you and the language. So if you write your code according to this memory model, it's guaranteed that it's going to be correct on all platforms that you run it on. Then the CPU, or the architecture that the compiler is compiling for, has a separate memory model for that particular architecture. So when you take your C++ code that's correct and free of undefined behavior, the compiler is going to compile it for a certain architecture, and then it knows, well, here's the model on that architecture, so this is what I need to do in order to uphold the language memory model that I promised to the compiler. Yes, so for the language memory model, since it's a C++ conference, we will use the C++ memory model as an example, but others are similar. Rust, for instance, it's almost identical to the C++ one. So Rust, they just love everything about C++, so they just took the memory model. I think C is probably similar. Does anyone know? I don't know C, but I would imagine it would be similar. So if you look in the standard, and I'll show you the entire section on the memory model, and I blurred it because we don't want to read it. The point is it's very short. This is like the entire memory model section. And it basically just says what's meant by a memory location. So that's a scalar type. It's like an int, a pointer, an enum, something like small like that. And then it says that two or more threads can access separate memory locations without interfering with each other. So if I have one thread over here doing some operating on some data, another thread working on some other data, well, that's just going to work. And that's basically it for that section. But if you want to know like all the things that we typically think about when you think about a memory model, you will have to also look into sequential execution, multi-threaded executions and data races, atomic operations library, and the thread support library. Then you'll get like the full view. Or Anthony Williams is here. You can just read his book, and it like describes it in human rather than in standardese, which helps. And then how can the compiler give you all the promises in all of these sections? It can give you that because it looks at the CPU memory model that it's compiling for. So any CPU that you're compiling for will have a different memory model, and the compiler then knows about these. So I'm going to use quite a lot of examples from x86 because that's, I guess, still what most of us use. And ARM and RISC-V are kind of similar, and I'm using RISC-V as an example because it's open source, which I like, and it's really well documented. Especially the memory model for RISC-V is really nicely documented. So you'll typically find this in the architecture manual for the CPU. And for instance, the RISC-V ISA manual says that a memory consistency model, which is just the same as a memory model, is a set of rules specifying the values that can be returned by loads of memory. So what does that mean? Well, you have a program, it's doing a lot of loads and stores to memory, and what would be valid values from those loads? And then in particular, if you have several threads, and this one does a store, and another store, and like if you load to that same location and other threads, like what would be valid, and what would not be valid. So, if you have one thread, it's actually very simple, because it's basically you load a pointer or like somewhere in memory, you load it, and then you store to it. Well, the store must not affect that load, right? You load the old value, and then you do the store. If you kind of a load and then you store, and then the load will return that store, that would be just meaningless. So that's basically all for a single-threaded program. And then that gives you this property that if you have a program and you have a given input state, that includes all input and like random numbers and everything that goes like into your program, there's only one valid output state. So that's very simple. And all the other output states are invalid because it's one thread, it's completely deterministic. If you have many threads, it's a lot more complicated. So there are like more things to think about. Because you can have any number of valid interleavings of threads. So one thread is printing 1, another thread is printing 2. The output is going to be 1, 2, or 2, 1. But it's not going to be a fork, right? It's going to be either of those. Those are valid. So you have program and input state, and you have several possible output states that are valid, and of course a bunch of invalid output states of the program. So what has the memory model ever done for me? And to see what the memory model is doing for you, we're going to use a bunch of examples. We're going to start with looking at the C++ memory model, looking at a couple of single-threaded examples, a multi-threaded example, and then talk about memory ordering. Then we're going to look at the CPU memory model, several variations, including x86 and RISC-V. So I want to start with a single-threaded example, just so that we can start like thinking about ordering of things. What are consequences of ordering in a program? And that's what memory models are about. Which assumptions can you make about the order of things in your program? So I've made this silly function here. It just has enough that I can talk about the things I want to talk about. It takes 2 int pointers, dereferences the first one into a result, increments the result, then dereferences the other pointer and adds that to the result and returns it. So it's basically just summing whatever the 2 pointers are pointing to and adds 1, and that's the job of this function. So if we annotate this with some pseudo assembly code, we can see here that it's, for instance, it's loading the A pointer into register 0. Then it's adding 1 to register 0 and storing that in register 0. Then it's dereferencing B into register 1, adding the 2 registers together, putting the result in register 0, and then returning that. This is just like pseudo-assembly. This is not an actual assembly language, just simplified. So then we have this function, and then we think about these 2 lines, and we think, well, loads are going to take time, right? They might have to go to level 1 cache. It's like 5, 6 cycles or something, or main memory, a couple of 100 cycles maybe. So what if we could get started on the load a little bit earlier, right? If you can switch the order of these 2, we can start the load 1 cycle earlier. Maybe we can shave an entire cycle of the function, so we can be a little bit faster. So can we, right? Can we swap the order of the add and the load? And if you look at the assembly here, we are putting 1 into 1 register, and we're loading something from memory into a different register. Like, there's no way that the output could change based on which of these you do first, or if you do them at the same time, or like it won't affect the program. So we should be able to swap these around, but let's just check the standard. What does the C++ standard say? It says that every value computation and side effect associated with a full expression is a full expression is basically one line in this particular function. It's sequenced before every value computation and side effect associated with the next full expression to be evaluated. So it's basically saying all of these lines happen in order. So like, can we swap them? Can we not? The standard does not dictate how to implement C++. The standard describes an abstract machine, saying that like, if you somehow run the program on this PDF that describes the C++ abstract machine, this is the output. And then as an implementer, you only have to observe the observable behavior of that abstract machine. So that means if you make any changes that would affect I/O, files, and volatile, and the implementation can add some more if they want, but like I/O, files, and volatile, if none of your optimizations affect any of those, then you can do whatever you want. So we can reorder these. Like, it's not possible for me to observe any changes if you reorder these lines. So we have the original assembly on the left and the reordered one on the right, where we swap the order of the add on the load. The load starts a cycle earlier, probably finishes a cycle earlier, and maybe we can shave a cycle of this function. So that is what the compiler could do, but the CPU could also reorder this on the fly, right? So all basically modern CPUs are out-of-order CPUs. So that means it can look at your machine code as it's running and figure out, I'm going to start on this one a bit earlier, or I'm going to put this on some queue, or like whatever. It can do whatever it wants. It's like changing the order of things as long as it doesn't break your program. Then the next question is, can we swap the order of the loads as well? So we have the load of A and the load of B into two different registers. Maybe for some architectural reason, architectural reason, there's an advantage in swapping the order of those. Can we do that? And I would say yes. We're loading two different addresses into two different registers, so it shouldn't matter which order we do those in. So the compiler can do that as well. Right. Let's see what GCC 15.1 with O3 does with this code. So here's my code, the C code to the left, and then the assembly to the right. And we can see that it starts by doing the two loads. So it's waiting with the +1. It's like starting with the loads as quickly as possible. I want to do both of those. And then in one instruction, it adds both of those values plus the constant 1 and puts it into the correct register, which is EAX, which is where you put the return value. So it can do all of that in one instruction. So thanks to being able to not necessarily do all of that in order, GCC figured out I can write this, which will be faster. So as long as you don't affect the output of the abstract machine, you can do whatever you want. OK, next example. Now I have two non-const pointers. I start by initializing a result by calling some getValue function that we don't see here. Then I increment the result. Then I store 2 to wherever A is pointing. And I store the result to wherever B is pointing. So the thing I got from getResult ++. And I put some pseudo assembly here again. This time it's very, very pseudo. It's calling a function and like everything in just one instruction. But it's like just to discuss orders here. And then as a compiler, I notice this line. I want to store a constant. It's like actually a constant expression I know at compile time that I'm going to store to A. And stores, they also take time, right? They have to go to memory. So then I figure maybe I can start the store a little bit earlier. Can we start storing A before we increment the result? Let's see, here's the original assembly, and can we reorder these lines? Well, they are completely independent. I'm just putting one into a register, and I'm like taking a value and storing it to memory. Those are completely independent, so I can store these two. So I can reorder these two, so I can do the store one cycle earlier. But like it's a constant expression. Maybe I can just do, that's the first thing I do. Can I do it before I call getValue? Nope. That's correct. Why not? Exceptions? Exceptions, memory model, several good answers here. Like Yes, get value could depend on A. So if the A pointer is pointing to somewhere that get value might read from, right, then we would actually affect the result of get value. And we don't know that when we just see this compilation unit. So we don't dare to swap the order of these because we don't know where A is pointing. It could be pointing into some data that get value is calling. So we can't do that. What about the two stores? Can we reorder those? They could be the same, yeah? A and B could be pointing to the same memory location. And if they do that, we must make sure to do these in order, because now it's supposed to hold the value of register 0. If you swap the order of these stores, it's going to suddenly hold the value 2 instead, like if A and B is pointing to the same place. So the compiler can swap these. But the CPU could actually do it. So the CPU could reorder the stores as long as they're not pointing to the same place. So your CPU is actually going to look at the addresses, and it's going to say this one is storing here, this one is storing there, and it's going to figure out, well, if these are going to different places, I can do them out of order, or simultaneously, or whatever you want, right? So the CPU knows more, because the compiler doesn't know where they're pointing, right? They could sometimes point to the same place, sometimes not. The CPU knows at runtime. So this is the best we can do. As the compiler, we figured out, like, I can't optimize any more than this. And then as the compiler, I have promised the C++ memory model to the user, so I have to be sure also that the CPU doesn't do anything more fishy, right? So I kind of have, as a compiler, I have to say to the CPU, do not store A before calling get value, in case it uses the same memory. And do not reorder these stores, like the order is important. And how do we express that to the CPU? Like, does the compiler have to do anything here? Let's see what GCC does again. So it calls get value, then it stores the 2, and then it stores the result plus, it stores that. And it's doing it in order. And it's just doing that. It's not saying anything more. It just says, put this value, like, call this function, put 2 over here, put this register over here in memory, and that's all. There's like, it doesn't have to say anything more to the CPU for this to work. And the reason it can safely do this without like putting any more careful instructions in here is the compiler knows that x86 will never reorder stores. If stores are in an order in your program, that's the order they will be run on the CPU. RISC-V can reorder stores. But still, RISC-V would only reorder the stores if they are to different addresses. So even on RISC-V, which is more free to reorder things, the compiler still doesn't have to put any like fences or anything, because then like it would just be too hard to write for a CPU that would be that relaxed in memory models. And when I say that the CPU could reorder things, that includes stuff from like the pipeline, caches, store buffers, like all sorts of microarchitectural details. So then I think it's time to start with a multi-threaded example. Now that we've started like thinking about what ordering means, because it's a memory model talk, I guess you're here for the multi-threaded stuff. And this is the example. It's basically the canonical example of for memory models, and also the canonical example of like lock-free communication between two threads. It's a very typical pattern where we have some data that's of some class that I don't know more about, like any sort of data, and a bool that says, is the data ready or not? Then I have a producer function which will run in my producer thread. It's going to initialize all the data, and then it's going to say ready equals true. Now all the data has been initialized. In the consumer, I'm just going to spin lock. While ready is false, I'll just loop around, waiting for ready to become true. And eventually, ready becomes true because the other thread wrote it, and I can use the data. Does this work? No? Which architecture? Well, on x86, it will look like it's working, but I would argue it's still don't do it. But let's look at the assembly here and see. Well, actually, no, not even on x86. The producer thread works, but not the consumer thread. Let's look at the assembly. So the producer, it calls initialize data, and then it moves one into ready, and we know that the stores are going to happen in order, so this is going to be fine. And the consumer, it's the while loop. Oh, where's the while loop? It just uses the data. It just optimizes away the entire while loop. So this clearly doesn't work. So why is the while loop gone? And in some years, you might get the while loop back, but at least currently, the while loop is gone. Yeah, it kind of changed. So let's see what happens with the while loop. We can think about informally. That first, just the intuition way of thinking is either this ready is always true. Well, a trivial infinite loop like this is, at least for now, in undefined behavior. So it's undefined behavior, throw it out. You could, no, it's always true, sorry, always false. Yeah, so if it's always true, you don't need it. You can just use the data because it's always true. It could be always false, which means then you have an infinite loop, and an infinite loop of this kind is undefined behavior. Or it starts out as false, then becomes true. That's what we want, right? That's the idea of the whole thing. And then there's a data race. So then it's undefined behavior, and we can also throw it out. So that's like, if you meet the compiler at a bar, this is the excuse the compiler is going to give you for why wait through out your while loop. Formally, it's about forward progress. So there's a rule saying that the implementation can assume that all threads will eventually terminate, do some I/O, or do some volatile or synchronization or atomic stuff. We're just reading a bool, so we're not doing any of those. So this thread is not making forward progress. So that's undefined behavior, and there's a proposal to change it for trivial loops like this. So yeah, this doesn't work. So here's a small change to our program. You can go back and forth. You see, the only thing I did was put the atomic around the ready bool. And notably, the data is still not the atomic. There is no mutexes around it, so the data is not in itself synchronized in any way that you can at least, particularly on the data, but the ready flag is now atomic. So let's see what changes with the assembly. In the producer, it's storing one in a slightly different way. This is an atomic store. And in the consumer, the while loop is back. Now it's loading ready into EAX. There's much lag on this pointer, and it's checking whether it's 0, and in that case, it jumps back. So it jumps around like this until the ready flag becomes true, and then it uses the data. So the data race on the ready flag is fixed, right? It's now an atomic. You can read and write from separate threads. But we're actually mostly interested in the data here. That's what we're trying to solve, right? Are we sure that the data has been completely initialized on the other thread by the time we see ready equals true? Are we sure that it's propagated through all the caches, store buffers have been flushed and all of that stuff? Is it safe to use the data, or is there a data race on the data itself? So we have to ask all these questions. Is the data initialized? Is the cache up to date? Is there a data race? Are there any microarchitectural details that we don't know about on any of the platforms that we target? And when you write C++, you don't want to think about any of this, right? That's why you want a memory model, so that the memory model can say, here's what C++ is doing, and I'll handle the microarchitecture. And the way to think about it is like this. If I have drawn the data on top here, the data and the ready flag, and here's the producer thread. It does initialize data, then stores the ready flag, and I have a nice monitor I can point down here. So yeah, and in the consumer thread, we will read the ready flag, and then we use the data. And the question you have to ask yourself in C++ is, did one thing happen before the other thing? So what we're interested in is, did initialize data inter-thread happen before use data? Which happens before relationship here. So that's what the C++ memory model is all about. Does an expression evaluation happen before another one? Or is there a data race? So what's a data race? First, we have to have this section saying 2 expression evaluations conflict if one of them modifies a memory location and the other reads or modifies the same memory location. And like conflict, that sounds like a bad word. It just means 2 things are using the same memory location and one is a write. But that you do that all the time, right? X equals 4, Y equals X. These two conflict. But it's fine. Right? It's not a conflict. It's not bad yet. So this is fine so far. But the execution of a program contains a data race if it contains 2 potentially concurrent conflicting actions. Right? Now you like using the same memory from 2 threads. At least one of which is not atomic. Right? So the data is not atomic. So we're still, like, it's a bit suspicious what we're doing. And neither happens before the other. So that's the important thing here. Did initialized data happen before use data? If it does, we're good. If not, there's a data race, since they're potentially concurrent, they're conflicting, and neither is atomic. Any such data race results in undefined behavior. So does the data write happen before the read? Does initialized data happen before use data? Is there a happens before relationship? So to do that, happens before relationships are transitive. So this is what you want to happen. Like if initialized data happens before ready equals true, which happens before while ready turns to true, which happens before use data, we will have like green, green, green arrow, like everything is good. But this is the non-atomic example. So unfortunately, it's not yet all green, or actually that's the next slide. Spoiled my next slide. The point is that within the thread, we saw previously that every expression evaluation, including side effects, happens before the next one. So inside of each thread, you have the happens before relationship. And then I wrote ready equals true here. This while loop loads the true from this ready flag, so it must have happened before. But it didn't, right? Not according to the memory model. So even though there's no other way, like we actually saw the value that was written by the other thread, it didn't actually happen before according to the memory model. Right? So we have no guarantees about caches and everything else being up to date. So there's no happens before. And then you don't have like a green line the entire way, so you don't have the transitive happens before. Then we just put the atomic around the bool on the ready flag. And then this line turns green. So that's good. Now we have what we want. Now initialized data happens before ready equals true, happens before we read the true over here, happens before use data. So now, even though there's no mutex, we know that it's no data race on the data. So why did the arrow turn green? Right? I said I made it atomic, and the arrow turns green. Is it just because it's atomic, or like why exactly is it green? So let's see what atomic means. Atomic stable guarantee that you don't get any half-written values. So if one thread writes a 64-bit word, then another thread can't observe only 32 of those bits, and then a bit later it sees the other 32. If there's atomic, you see nothing or everything. Also, there is a total order to modifications to every individual atomic. So if I have one atomic, all the threads have to agree on the order that that one is modified. But if you have several atomics, and or anything else, any other questions you might ask, it depends on the type of atomic you're using, or the type of atomic operations you're using. So just that it's atomic is not the thing that saves us. So here's the correct solution again without UB, where we use this to the atomic. This is shorthand for this. So when we said ready equals true, what we're actually saying is we're saying ready.store memory order sequentially consistent. So now we're specifying a memory order, and the default that you just get behind the scenes is memory order sequentially consistent. And in the load, when we're reading ready, it also uses sequentially consistent memory order. And that is actually the safest of the memory orders, and not necessarily the most performant one, but it's the default. So in C++, you get like the safe thing as the default. I think that's pretty cool. That's not often, but we have it here. But you often don't need it, right? So if you want, you can opt out. Like imagine if vector was like checked and then at was the one you could choose to do if you wanted to have the unchecked. Like that would be so much nicer, but too late. But this is actually nice. So I said memory order sequentially consistent. What does that mean? It establishes the happens before relationship. So this is exactly what we need, right? We want that arrow to be green, and so this is what we want. Like if one thread observes a store from a different thread and they're both using sequentially consistent, it did happen before, so then you're guaranteed that like all the caches are up to date and everything. It also says for all the sequentially consistent operations in your entire program, like on all threads that don't have anything to do with each other, there's one single total order of all of those operations. And that's maybe a bit stricter than necessary. That's not what we need here, right? We could have some other threads working on some other data, and we don't care about the order of things between these threads. We want to be a bit more specific, maybe. On the opposite end of the spectrum, we have the relaxed memory order, which does not establish the happens before. So if we use relaxed, the arrow is now red. Even though it's atomic, the arrow is now red. And yeah, it has the one total modification order per atomic, but not among atomics. And no matter the memory order, you always avoid the half-written values. So again, here's the correct solution, where I've removed the shorthand ready equals true and shown like the full ready.store with sequentially consistent and ready.load sequentially consistent, which makes the arrow green because of sequentially consistent, not only because it's atomic. If I use relaxed, the arrow is now red. So now there's no happens before relationship. So there's no guarantee on the data anymore that the data has also propagated. Yes, but we figured out that the sequentially consistent might be a bit overkill. We can't use relaxed. So let's see what can we use. We can use acquire and release memory orders. And it says here that if an acquire load observes the value of a release store, the release stores happens before the acquire load. That's exactly what I want, right? If I store ready equals true, and then the load in the while loop observes that store, then it happened before. And this is then that makes the arrow green. This is what I'm after. So this sounds nice. And yeah, it is nice if I use release on the store and acquire on the load. Now there's a happens before, the arrow is green, and this is basically as good as you can get it. So the store happens before the load now. And like the way this works then is that you can't reorder, neither the compiler or the CPU can reorder any of these stores after this. Because we have the transitive happens before. So now that I do this, it's kind of like a little stop in the CPU where it has to make sure that all of the other stores have become visible. And also here, the acquire load, I can't start doing any of the use data loads up here because there's an acquire load, so it's kind of like a stop again, like wait until this one has actually come through, and then you can do all the other loads. And the names release and acquire, the way to remember them is to think about mutexes. So if this was done with mutexes, this is where you would release the mutex when you're done writing, and this is where you would acquire the mutex. This isn't a mutex, but the names kind of go in the same place, so it's how you remember what these names mean. So this. Yeah. OK, so let's look at the multi-threaded example yet again on x86, where we now change to using memory order release and memory order acquire for the store and the load, and see what the assembly looks like. So on the producer thread, it calls initialize data, and then it stores ready. And now, like on the default example, it actually used an atomic store. Now it just uses a normal store. There's no trace of the atomics here anymore, even though we're using an atomic with a memory order release. And the consumer also has a non-atomic load. And yeah, the while loop is there and everything is fine. And the reason the compiler could do this without like putting anything specific about atomics in here is because it knows about the x86 memory order. So it knows none of the stores are going to get reordered. So all of the initialized data stores are going to be visible to other threads before the ready flag becomes visible, even though there's no atomic prefixes, lock prefixes, or anything fancy. Yes, so if I were to change the memory order here to relaxed, I would get exactly the same assembly. But I wouldn't have the happens before, and now there's undefined behavior, even though the assembly looks completely identical. The producer thread here is also exactly the same as if I just had a bool, which is not non-atomic. So if you ever you have some code and you try to play around with the atomics and you see, well, the assembly is the same, it must be safe, don't do that, don't trust the assembly. Because there's still undefined behavior in your program, a future compiler could maybe do something fishy, or you port it to a different architecture. So that's the comment we got earlier from here, saying, is there undefined, or does it work? Depends on the architecture. On x86, it would seem to work if you put relaxed, because it's so strict about reordering. But then you compile for ARM, and you have some pretty interesting debugging hours or weeks in front of you when this happens every billionth time at a customer somewhere. So yeah, don't trust the assembly when you think about these things. Yeah. Just for completeness, there are two other memory orders as well. The acquire release, so if you have a read, modify, write operation that needs to both read and write, this might come in handy. And then there's consume, which you can just avoid. Yeah, so how does the compiler know then? Like for x86, I don't have to put anything. For RISC-V, maybe I do. For ARM, maybe I do. And we've said that a few times now. It's because of the CPU memory model. So this is what the compiler needs in order to support the C++ memory model on a particular architecture that it's compiling for. So what do we mean by reordering on the CPU? It could be out-of-order instruction scheduling, out-of-order micro-ops. So like one instruction can actually turn into several micro-operations on the CPU, and those can be even reordered. The pipeline could have some effects on this. Forwarding networks, store buffers, store and load coalescing, the memory system, caches, like all of these things that are particular to each CPU, not even only to the CPU family, but sometimes it's like different on the models as well. And like we don't want to think about all of that. Like even the compiler doesn't want to think about all of that. And even the people who write like runtime concurrency libraries and whatever, who has to do a bit of assembly, they don't want to think about all of this. They just want a memory model. And in the CPU world, they often say memory consistency model. It's just the same as a memory model. And this has a different way of thinking than the C++ memory model. So in C++, we've seen many times now like the arrows. Did this expression happen before the other expression? So we have to like imagine like there's an order of all the expressions across threads. Like, did this happen before this one? Did this happen before that one? In CPU memory models, what you typically do is that you imagine one single global order of all memory operations in the entire program. And then you say, what are the allowed orders of these? And there's a book by Sarin, Hill, and Wood, a primer on memory consistency and cache coherence, which has this drawing. And it's illustrating a bunch of cores C1 to Cn. And then it says, imagine that the memory is a single box with a switch in front of it that picks in an arbitrary order memory operations from all of the cores. So only one core can do one memory operation at a time, and it finishes before the next one. This is not how a CPU works. Of course, that will be incredibly slow, but it's the mental model. And then you have it's just a model thing again, so that the compiler, or if you write assembly, you can imagine that it works like this. And then the microarchitecture can do whatever as long as it follows the memory model. And then like the question then is like how what are allowed reorderings inside of this switch kind of. So here is the data and ready example again. It's just now it's in assembly. The data is just a single integer value 42. So we put the 42 into register 0, and then we store register 0 to wherever data is pointing. That's our entire data, just the value 42, just so we don't have to have so many instructions. And then I put 1 into register 1, and I store that for the ready flag, wherever ready is pointing. On the consumer thread, I have this wait label. I load ready into register 0, and I check, is it 0? Oh, then I jump back to wait. So I just keep jumping around like this until register 0 finally loads true. Then I can load the data into some register and use that register. So now I can use the data. And that's the program order. That's the order that the program is written in. And then you have this switch that picks memory locations. And it only cares about the memory operations. So when you think about the memory model on the CPU, you only think about memory operations. So we just remove the other ones. So we only have these two. And then we say, what is a valid order? Right? If the switch picks memory orders in some order, what would be a valid order? So in the imaginary global total order of all memory operations, imagine that each thread takes turns. And there's like as if, because it's not doing this, like everything is going caches and stuff, but you imagine that each thread takes turns. How much of the program order is preserved into this global total order? Right? That's the main question of a CPU memory model. So if you look at the memory order, like this is one example of a possible memory order. Right? You have that thread, the producer thread, the consumer thread. In this example, the producer thread happens to finish entirely before the consumer thread starts. So this could be a memory order, right? You can have the store of data, and then the store of ready. Then you load ready, and it's true on the first try, so we can just load the data. That would be a perfectly valid memory order. Here's another possible memory order. We store the data. We load ready, it's false. We load ready, it's false. We store ready to true. We load ready, now it's true, so we load the data. This is also fine, right? That would be kind of what we expect. We write the data, and like the consumer thread starts like waiting for the data, and suddenly it becomes ready, and it can use it. So this could also be a possible memory order. This could also be a possible memory order. We load ready, then we store ready. Even though we're supposed to store data first, we store ready first. We load ready, it's true, so we load the data, and then we store the data. And now the data is not up to date. But this could also be a valid memory ordering. And that's the main question of that the CPU memory model will answer is which of these examples of memory orders would be okay? Because it says how much of program order will be preserved into this memory order. So if the data is stored before the ready, is that order preserved into the actual memory order? And, It was really cold sitting down there at the keynote, but up here is a lot warmer. Anyway, so the simplest memory model you can think of for a CPU is a sequentially consistent memory model, where everything from the program order is always preserved in the memory order. All the program order is preserved. It's easy to reason about, but less possibilities for optimizations. So basically, no one does a full sequentially consistent memory model on a high-performance CPU. And in the sequentially consistent model, you could not reorder anything. So the stores have to happen in the same order, the loads have to happen in the same order in the memory model in the memory order as they happen in the program as it's written. So if there's a load before a load, you can't reorder. A store before a store, you can't reorder. Load before a store before a load. Any combination of these, you can't reorder anything. All these orders have to be preserved. But that's not the fastest way to do it. So what x86 is doing is to preserve everything except store before a load. This is also known as total store order. So that's like the academic term. x86 doesn't actually document the memory model. So you can't really know. But like academics, they say, well, we think it's TSO. So we just treat it like that. And it basically, they're probably right about this. But what they both say then is that if there's a store before a load, you can actually delay the store a bit. And this is motivated by store buffers. So if you're a CPU, like you have all these instructions, there's a store instruction, you don't have to wait for that store to get all the way to memory before you can continue with the other instructions. You can just stick it in a store buffer on the core, super fast, and then you just keep running, and eventually the store buffer will be flushed out to memory. But then in the meantime, other loads could happen. So the store could be delayed a bit to go after some of these other loads. And if you have a later load to the same location that you just stored, you can just pick it up from the store buffer on the CPU. Like, you store to address 42, you load from it. Oh, it's right here in my store buffer. I already have it. I don't even have to go to cache. So that's a bit faster than sequentially consistent. And what they often do when they want to talk about these memory models is they have these litmus tests or these kind of small examples of what would be valid or not. So this is the one that you tend to see for TSO. You have two threads. They're both storing a value, and then the other thread reads the value that the other thread stored. And then they ask, can X and Y be 0? So if you think like sequentially consistent, all of program order is always preserved. Like, how could Y be 0? It must be because the store hasn't happened yet. So then that goes before this, and since program order is always preserved, then that means this must have happened before I read the 0. So, and then this store happens, and then by the time we get here, X is 1. So if you have sequentially consistent, you're not allowed to reorder any of the program order into the memory order. It's impossible on sequentially consistent for both Y and X to load 0. But on TSO, it is possible. Because you can order a store, you can reorder a store after a load. So you can do this, where you load 0, then you store 1 here. Then this X hasn't been stored yet, so it's also 0, and eventually we do the store. But now this program order has not been maintained into the memory order. And that you can do on TSO, on x86, but not on sequentially consistent. So one small clarification here then, that at least tripped me up, so it will probably trip others up as well. What if I store and load from the same location? And the memory model says, well, you can do the store after the load. Then suddenly the load would return the old value. This would be bad, right? Can the store of X be ordered after the load of X? We just said that you can do that, and in the memory order, like in the theoretical memory model, that actually can happen, right? You're allowed to insert the store after the load into the memory model. So you can do that, but the value of the load on that particular core will be the correct one, because the memory order is the order that the memory operations go to this hypothetically serialized switch to memory. But the value of a load follows the program order first and then the memory order. So even if we do this, by the time we do the load, it has to follow the program order for the actual value. So it's going to pick up the load from the store buffer if it hasn't been flushed out yet. And then, this is just theoretical. It probably never even goes to the cache in reality. I think that's a bit confusing, but that's how it is. Yeah. So it's just a model. That's the point. And then, now that we've seen the CPU, the TSO or the x86 memory model, we can realize why this is fine to just use regular stores, because we know that x86 and TSO, they're never going to reorder stores, so we don't need to do anything specific. And it's not going to reorder loads. It doesn't have to do anything specific. We can just store and load to memory, and everything works. But then the question is, do we really need to keep the order of all the stores and all the loads that happen before a store? Why are we only allowed to reorder a store before a load? What if I want to make a CPU with a non-FIFO store buffer? What if I want to have coalescing of stores and loads? I want fancy speculation and memory prediction and other optimizations in the memory system or in the cache. Do I really have to be as strict as TSO? And to look at, see a demo how that would make a difference, we have this example. Now we're doing the data is 2 words instead of 1. So we have data 0 and data 1, and then ready. So what we care about now is that Like, I don't care about the order of that the data is stored as long as both of those happen before the ready flag. So this will be fine. Here I have reordered data 1 and data 0. So the data is stored in like whatever order, but they both happen before I store the ready flag. And the same here, I have to load the ready flag before I start loading the data. So that's what I care about. I don't care about the order of the individual pieces of the data. So TSO x86 would never do this. On more relaxed memory models, we would allow that. So this could potentially be faster. If you happen to have like write permission on the right cache line for one of them, but not for the other, you're just like, okay, let's get that one out of the way, stuff like that. So I care about data with respect to ready, but not data with respect to other data. So then as a programmer with an interest in performance, I want to give the architecture a lot of freedom to optimize. And I want to tell it which memory operations do I actually care about, so that it can just like go ahead and do whatever with the rest of the memory operations. But I want like a few safe defaults, right? So I don't have to put a fence between every memory operation in my entire program. So then I need this memory model to reason about. And we saw that x86 had this memory model where you just said you can do a store after a load, the rest is preserved. So like everything is preserved except one thing. But RISC-V, for instance, says nothing is preserved except a few things. So it's kind of the other way of thinking about it. So one example from RISC-V is if you have a data dependency. So if I do 2 stores to data 0, it's going to keep that order. Like if I write x equals 2 and then I write x equals 3, if I had to like put a fence in between, like it would just be too dumb. So like let's not do that. If there's a same address, store to store, keep the order, please. And similarly, if there's a data dependency, so I load some data into register 0, and then I store register 0 to some other data. So I do a load, and I take the thing I loaded and store it somewhere else. Again, there's a clear dependency here, so RISC-V says, let's keep that one. So that's guaranteed to not be reordered. Or if there's an address dependency. So I load a pointer to figure out where I'm going to store something, and then I store the value to wherever the pointer was pointing. Now you have an address dependency, so RISC-V also says, we'll just always keep that for you, so don't worry about that. You don't have to put fences or anything. So if I am the compiler and I want to write this on RISC-V, I have to emit some fences. So now RISC-V says, as long as these data pointers are pointing to different places, I can just do whatever. But here's a fence, so let's wait until all the stores have actually like gone into the memory order, and then I can store the ready flag. And on the consumer thread, I load the ready flag, but there's a fence saying that I have to wait for that load to finish before I start loading the data. And this is how the compiler would then write machine code for the C++ example we saw in order to make it safe. But now the data can be reordered. So yeah, x86 preserves everything except store to load. RISC-V allows all sorts of reordering, except 13 specific rules. So don't reorder past the store to an overlapping place. And all these dependencies that we just saw, you keep those. And on the fences, that's the important part. Like you put a fence when you like want to say pause, finish everything before you continue. And then atomic memory operations and like a few rules like that. Don't worry about the details. The point is just everything is allowed except 13 specific things. So it's in the ISA manual. So in summary, you as a programmer, you care about the language memory model, right? You write correct C++, and then it's going to work on all architectures. And then the compiler and whoever writes assembly for runtime libraries or whatever, they look at a particular architecture memory model for the, now we're compiling for this architecture, so let's look at that memory model to make sure that we can uphold the language memory model that I just promised to my user. And then someone is making a CPU for this architecture, so then they have to design their architecture with their pipelines and store buffers and all of that, cache coherence. They have to get that right so that they uphold architecture memory model. And then they want to just be as fast as you possibly can and do any sorts of weird optimization tricks as long as you conform to the architecture memory model so it doesn't break. And this is what CPU designers often spend a lot of time thinking about. So the two things to remember. In C++, you have to, when you think about the memory model, you have to think about, did this expression evaluation in one thread happen before this expression evaluation in the other thread? Is this arrow green or red? For the CPU memory model, it's this mental model instead, where you have all the cores and you have a switch, and it's like kind of in some arbitrary order just picking memory operations from each of the cores. Yeah, so then you have like the program order for all the threads, and then they all go into one order. And you say, like, how much of the ordering in the program itself is kept in this imaginary global total order of everything. And bonus thing to remember, don't trust the assembly. Like we saw that we have the correct UB3 program. We changed from release and acquire to relaxed. The assembly is exactly the same, but now we have UB, and it's going to break on ARM. And that's it. That's the two memory models. Thanks a lot for coming. And then we have actually time for a few questions. Just going to switch the water bottle.
So we have a question from online. We have always been using default memory order while using atomics by not explicitly specifying the memory order. Are there any inherent dangers while using atomics if we only use default memory models and if our software is designed to be multi-platform?
If you use the default, you just say ready equals true, you get the safe, nice, sequentially consistent one. So then you're safe. Just do that. And if you want to try to optimize, you can see if you can find something that's faster, as long as you make sure you're still correct, and then you benchmark it. And Thread Sanitizer can probably help you if you do it wrong.
Thank you.
So you were talking about x86 and RISC-V, and from my understanding of your talk, those are kind of the extremes. I'm kind of curious, like, are ARM or other processors kind of more similar to RISC-V? Are they more similar to x86?
Yeah, ARM is more similar to RISC-V.
Okay.
It's also relaxed, so you'll see like more messages from the compiler to the CPU in ARM assembly than in RISC-V. But I'm not really great at ARM, so but it's more similar to RISC-V in that it's a relaxed model. Any other? One more from online.
Yeah, so we have a second question. Does CPU memory model can override programming language memory model? For example, if we use default memory order in our program, will CPU use another memory order by its own?
Yes. So the names are the same often. Like you have the sequentially consistent C++ memory model, and you have the sequentially consistent CPU memory model, but those mean different things. On C++, it means like all of your atomic operations go in a single order. Stuff on the CPU, it means like that all memory operations go in order, not only the atomic one. So they mean a bit different things. So yeah, it means different. Like you can compile a sequentially consistent C++ memory model on a much more relaxed ARM or RISC-V memory model, and it's going to work because the compiler will add the necessary fences. So it's going to be safe.
Thank you.
Hi, nice talk. Once upon a time, there was an effort to put transactional memory into C++.
To put what?
Transactional memory.
Oh, right. Yeah.
Has this gone anywhere? Are you like?
I am not
knowing?
aware of that. I haven't been following transactional memory, so
yeah.
I don't know.
Gone nowhere. So, okay.
Thank you for the talk. So if you have several atomic variables using different ordering, then how it will be consistent then?
Yeah, so if you have several atomics with different, or several operations, even on the same one with different memory orders, it's going to, the memory model in C++ talks about like each of the operations you make on it. So if you have this particular store, is a release store, and this particular load is an acquire load, and I actually observed that value that you just stored, then it happens before. Later, you can use the same atomic even with a relaxed memory model. And then if like a relaxed load then sees the same release store, it doesn't happen before anymore. So the way to think about it is only between two specific expression evaluations. Did one of them happen before the other? So you can have, also you can have like one atomic that's using only sequentially consistent between some threads and another one that's doing only relaxed, or like one atomic can use a mix. And it's always only about each particular expression using that single atomic. Yeah, it's 15 past, and it's quite late in the evening. People are probably hungry. So time to close, I guess. All right, thank you.